Hello, welcome back to Quantum Computation Explained. I'm Kadiresan. In this video, we will learn about quantum image processing, specifically about how to encode an image in a quantum computer and how to do edge detection. Okay. I'm sure most of you are aware what is image processing and how is it done and where it is being used. But for those who do not know about that, maybe we'll take a minute. Image processing is the process of performing certain operations on an image to get some useful information from it. Okay. So what are the processes we can do? So it can be classification, feature extraction, pattern recognition, and projection are some of the image processing techniques. Of course, there are many more we can think about. Where is it being used? It has got wide applications: medical imaging, surveillance, remote sensing, robotics, augmented reality, virtual reality, biometrics, character recognition, inspection. Of course, this is a very recent addition. A lot of inspection activities in the factories are being done. Entertainment, I mean, like that. People are coming out with different applications. So it's a proven algorithm or a proven system we have in classical computing to do image processing and applying it to some necessity like medical imaging, correct? So why should we bring quantum computing for image processing? Okay, there are some advantages, likely advantages I would say. Particularly if you take for edge detection, using quantum computing, we'll be able to identify the edges in time complexity O of n, where n is the number of pixels in the image. This is much faster than the classical algorithm actually, which approximately takes n square. And in certain worst case, because it depends on the algorithm what we use, it can go as high as 2 to the power of n. More than that, there is another very big advantage in using quantum computer, that it has got the ability to process large data sets. Right? Suppose we have 10 qubits, we can handle easily 2 to the power of 10 pixels easily. And if you have 100 qubits, you can imagine the size of the image what you can handle. And if you have 1000, so it goes very fast, right? I mean, the size of the image what we can handle in a quantum computer, which cannot be even thought about in classical way. But you can't really compare. The quantum and classical edge detection algorithms are not directly comparable. Only on the basis of time complexity bounds what we saw just now. It's because to make quantum algorithm work, the number of measurements one has to do to get considerable accuracy of the algorithm is very high in NISQ. So what is NISQ? So what is there today, correct? We have noisy quantum computers, so we cannot really do a large computation. So certainly we can't claim today quantum computing is much powerful compared to classical computer for image processing, but certainly one day it will be, once we have sufficient number of qubits with less noise or no noise, there will be big advantage. That's the reason we are trying to learn now. Okay. So the first thing we should know is how do I represent a given image in quantum computer, correct? So that's the basic thing we should understand. But before that, let's have a quick recap on how is it being done in a classical computer. We know that raster or bitmap format and vector-based image formats are the most common representation of an image in classical computers. And there are different ways to do that. Images in classical computers can be stored in different ways. The simplest one can be as matrices of intensity values present in every image pixel. For example, let's take this image, so which is handwritten 8. So, and this can be represented by a matrix of elements, where whenever there is black color we will put a 0 value, and when there is something white we'll have some on 255. So what is that 255? Because we are trying to work with a resolution of 8 bits. Okay, and anywhere in between you have grayscale, and the value will vary from 0 to 255. In quantum computer, what we'll do there are many ways of representing images in quantum computing. So some of them are getting listed here. The first one is called FRQI, flexible representation of quantum images. Some people call Fourier reconstruction quantum imaging. NEQR, QPIA, qubit lattice, real cut representation. Like that, there are many methods. Still people are coming out with new techniques. You can also come out with a very nice way of representing image in a quantum computer. What you need to consider is, it should, if it uses less number of qubits, it's good. If it is easy to work on it, then it's better. And finally, if it gives very accurate output, that will be the ultimate one. So considering those aspects, people are trying to improve the ways of representing images. So this is just a comparison of different methods. We don't have to take it very seriously. This output has come from board. And you will really, you will be able to really specify the advantage and disadvantages of these three methods. So let's start with FRQI. So it requires the fewest qubits to encode an image. It is also the least accurate, and it can be difficult to recover the original image from the quantum state. So let's see why. Why it's less accurate and difficult to recover the original image. So basically, it needs 2n plus 1 qubits. So what is n? N is taken from picture size 2 to the power of n into 2 to the power of n. Not the image is given as n by n pixel. So remember that. So by this method, if we are able to encode, then the state of the set of qubits will be represented by this equation. So what are the terms here? So you have qubits, which gives all the possible combinations for the given number of qubits. For example, if we use a 2 by 2 image like this, so how many qubits are there? So it is 2 to the power of 1 into 2 to the power of 1. So n is 1. So we need 3 qubits. So out of 3 qubits, 2 qubits are used to index the pixel, and 1 qubit helps us to encode the intensity. Okay. So typically it will look like that, right? For 2 qubit system, we'll have 4 possible states like this, and for each of the states, we will try to associate a phase to them. So for example, this picture which is having 4 pixels. The first one, what you see it on the leftmost, which is black. So we will encode it with 0, and this we will encode it with 1, I'm sorry, this will be encoding with, yeah, not 1, will be encoding with the pi by 2, and other 2 pixels which are, gray color, so they will be encoded with some angles in between 0 and pi by 2. So after we encode, if we measure the state of qubits, you will get the output something like this. Okay, so here how do we read this output? From the right side, the first 2 qubits, they represent the indexing. Okay, so 0 0, that is this one, which is having complete 0, which means it is total black. Similarly, the bottom right one, we will have 1 1, which is completely white, that's why we have 1 here. And what about these two pixels? So this one is off white, off black, so which is nothing but 0 1. Okay, we have to read like this. So they are almost equal, right? This 0 and this 1. Whereas this one is having more black, that is why you see the probability of getting this as 0 is higher compared to 1. Okay, very simple approach. Okay, now what are the drawbacks? The drawbacks are, maintaining the angle is not a good thing, it's less accurate. Another thing, after manipulation or after the image processing, we need to get back some image, correct? So at that time, we will be having an issue, but, added issue, I would say, because we need to do some invert QFT, Fourier transform. So that's why it is not frequently used, but very easy to implement, easy to understand. Alright, so we'll go to the next one, the novel enhanced quantum representation. This is more accurate than the previous one, NUQR, and it can be used to recover the original image from the quantum state more easily. However, it requires more qubits, so this is important. So how it's going to be encoded? We'll be having 2 registers, one for the positioning or indexing, like what we had in the previous method. But the intensity of the pixels are totally encoded in another register. Okay, so that the size of the register or the number of qubits what we'll be having depending on the resolution what we are interested in. So for example, 0 to 255, which is the standard way of specifying the gray scale. So we will be having 8 qubits to represent, correct? So in this approach, the state can be represented like this, wherein this will be the index like 0 0 0 1 1 0 like that, and this set of qubits will represent the grayscale intensity. So the grayscale intensity is given here: 0 black, 255 white, 100 this one, and 100 is this one, and 200 is a light shade. So this has to be converted to binary form, and that's how we will be encoding them. So after encoding, if you make a measurement, you will get something like this. So wherein the first 2 qubits indicate what they are: 0 0 1 0 0 1 1 0 and 1 1. You can see here 0 1 is 100 and 1 0 is 200, represented in decimal form. So we can see they will be very accurate, they don't get disturbed easily, but the drawback is we need more number of qubits, and particularly when you are working with color pixels, you need like this three times, right? One for R, one for another one for G, and the last one for B. So the number of qubits will increase. Okay, we'll move on. Quantum probability image encoding. Okay, this also needs very less number of qubits. So that is one more interesting thing. And in this approach, well, let's say n is the total number of pixels in an image. We'll say this small n is log of n to the base 2. You may wonder why there we put it in a different way and here we are representing in a different way. I mean, that's how most of the papers they do it. So I'm also just following it. But it's up to you to decide. So only thing we need to understand the concept. Okay. So the image represented is still in pixel intensities converted to probability amplitude. So this is very important, not phase of a quantum state by normalizing so that the sum of the squares of all probability amplitude is 1. Assuming that this represents the intensity, what you need to do is for each pixel intensity you have to divide by square root of sum of intensity squares. So that is what we call it as normalization, correct? Why should we do normalization? Because the squares of all probability amplitudes should be 1 and that's what will happen. Okay. So typically a 2 by 2 image can be represented by qubit state like this. So as usual we'll have 4 indexing qubits and to that we are going to add some probability amplitude. So we can also write an equation like this, I equal to 0 to 2 to the power of n minus 1. We know that there will be n states and each qubit will have an associated amplitude. So if we take our standard image with 4 pixels, this is with 0, 0, right? So here you don't see anything mainly because it has got 0 amplitude, whereas this one is having less amplitude. It increases slightly for C2 and for C3 has got the maximum amplitude. Good. And it's very simple to do that. And we have seen each one has got some advantages and disadvantages. Okay. And for our edge detection, we are going to follow this method. Yeah, I'm sure again most of you are aware what is edge detection. It's an essential method to identify components of an image. Suppose we are given a large picture, we need to identify, and if there are many objects, we need to first to do edge detection and then we will be able to identify. Classical edge detection algorithms rely mostly on computation of image gradients. So this is typically an image with like, a cat on it, and this is the edge detected image. You can see here whenever there is a change in the pixel intensity, so we will identify it, and that's how this image is generated. QHED algorithm uses the action of Hadamard gate. So we are familiar with Hadamard gate, right? That's the most wonderful, powerful gate which converts the basis state 0 and 1 to superposition state. Here also it's doing some wonders. So let's try to understand what it does. We need to apply hatch gate for the least significant bit. So if you have 2 pixels, don't do anything with the first pixel. So put an I gate or multiply with identity matrix. So this is nothing but Hadamard gate, right? The unitary matrix for Hadamard gate. So when you multiply I with H, you will get another unitary matrix, something like this. So this one, we will be operating on the state of the qubits. So what you see here, I'm sorry. And we know the state of the qubits are given by a row vector C0, C1, C2, C3, correct? All the four possibilities with their probability amplitudes getting listed here. So we are going to apply Hadamard gate to the LSB, which will have an action something similar to adding a unitary matrix like this to this row vector. And interestingly, when you it's simple matrix multiplication, you are able to see some gradient, right? So this is how the Hadamard gate helps us to do. Okay. We now have access to the gradient between the pixel intensities of neighboring pixels in the form of Ci minus Ci plus 1, where I is even. So this is an important point, because you can see here C0 minus C1, C2 minus C3. So you are starting, I mean, if you have a larger size of image, you will have something like this, it goes on. But the important point to be noted here is it's giving the even pairs, correct? It doesn't give C1 minus C2, but we need that. So to get gradient between both even and odd pairs, we will add an auxiliary qubit and a H gate to it. So when I add an auxiliary qubit and H, okay, so let's say initially we have some n qubits, and their probability amplitudes are given like this, correct? So now we are adding one auxiliary qubit with a H gate onto it, Hadamard gate. So when you do the multiplication, we know that the size of this row matrix will get doubled, correct? And what are the new elements? They are nothing but the old elements getting twice, correct? That's what will happen. Now we need gradient. So how do, and we need gradient for both odd and even pairs. So for that we are going to do another trick, and the trick, it's called amplitude permutation. So amplitude permutation actually is a very common word to do multiple quantum image processing, but in this case we are trying to do one simple trick. So we know that there are two Z0s like that, all elements. One C0, we are shifting it to the end with the help of this amplitude permutation unitary gate or unitary matrix. So how to get this? This is nothing but the first row, sorry, first column, the last element should be 1, and for the next column onwards, you just start from the first one and then move on to second, third, like that. Okay, and this is easy to implement with simple gates. Okay, we will see it later how to do that. So when you do this, C01 which was here, it got shifted to this, and now when you add a Hadamard gate to that, you will see C0 minus C1, C1 minus C2, all differences, both odd pair and even pair, we were able to get. So maybe in summary we can say, depending on the size of the image, we will take so many number of qubits and we will encode them with probability amplitude, and the trick to get the gradient comes from the auxiliary qubit, wherein first we will add H, for what H will help us to double. Okay, and then this entire thing is actually permutation matrix, and the last H, so this will help us to move one C0 to the end, and this H will help us to get the gradient. If you want to understand more, you can see this web page. I have taken this picture from here. So one more thing you should have noticed, we are trying to take from here the difference gradient, but we are not seeing like this, meaning vertical scan or vertical edges we are not finding out. So in order to do that, we need to do some simple operation. We just take the transpose of the image and repeat the process. So now you will get a set of vertical gradient. Okay, very simple. The horizontal and vertical scans are then superimposed on each other using some classical post processing to create the full edge detected image. Maybe you can see with an example. So this is the original image. So first we will be seeing the horizontal gradient. One here, yeah. Here you will see the difference, right? So when you do the horizontal scan, you will see 4 here, 1 here, then again 5, 2 like that. Similarly, we can do vertical scan, and that is given here. And when you superimpose, you will get edge detected image. Very nice, right? Simple. With simple tricks, Hadamard is really doing wonders. Alright, so maybe we can have a look at the code to understand better. Let me try to run it. So this you are familiar, well-known functions. We need to import. I also brought some NumPy stuff here. Okay, and then Python's matplot library. So the image is given like this. You can see here the first row is full of black and the second row is having 3 black pixels. So like this, first and the last two. So we are able to represent the image what we want to process or what we want to do. Edge detection is given here in an array form, and we are just plotting it. Now this function helps us to do amplitude encoding. Actually we are not going to do the encoding here, we are only going to get the values which have to go into the amplitude encoding, right? So first we need to do normalizing. So that is what is being done here, and in order to do normalizing we need to get the square root of sum of square of all the amplitudes. So that is what is being done here, and that is arranged to another array here. For we have to do it twice, right? One for horizontal scan, another one is for vertical scan, and vertical thing is simply nothing but the image into transpose. We have seen it earlier. Now how many qubits are required? So it's because of the size, which is 64, right? 8 by 8 pixels we had. 64 can be easily represented by 6 qubits. 2 to the power of 6 is nothing but 64. And we need one ancillary qubit. So the total qubit will be 7. Now we are creating the circuit. We'll be generating 2 different circuits, one for the horizontal scan and another one for vertical scan. Okay, and we are initializing. So this is one of the very useful functions. I have not used earlier, first time I'm using. So wherein if you know the amplitude factor directly, the function available in QISKIT will be assigning the proper amplitude to different states what is required. And similarly, this is another function which is very useful, wherein if you are giving the values, it will generate the unitary matrix. Okay. All right. Then we need to apply. This is for the shifting of one C0 to the end, right? And this is for doubling the number of elements, and this is for gradient generation. So similarly, we are doing it for vertical scan, and finally the circuit will look like this. You have encoding portion here, then Hadamard, unitary matrix, then another Hadamard. That's how the circuit is done, and we need to repeat the circuit for vertical scan. and when you run it, you get some numbers, correct? So that has to be converted back to 0 and 1 for plotting. So that is what is being done here. So depending on the value, we are just declaring a threshold. If it is less than something close to 0 or above 0, we are declaring either it is 0 or 1, and later we are plotting. So I think this, you have seen it earlier, horizontal scan, and this is vertical scan. And now here we are going to merge the two. Okay, so this is the original image, this is merged one. So we are able to generate an edge detected image which can be used later for any recognition or identification of an object. Okay, so maybe we can have a quick look at the encoding code. FRQI encoding is done using this angle I told you earlier. 0 is the black and pi by 2 is for white, and for gray we can have something like anywhere in between 0 to pi by 2. So the quantum circuit, we need to first generate, I have Adamant gates to create superposition, which will be used for indexing the pixels. And now we are going to apply the corresponding angle. So for each of the states, that is what is done at 4 places, and the final circuit will look like this. So nothing great about that. So Adamant gate to create superposition. So this gate is useful for adding the angle to the respective qubits. Alright, so 0, literally we are not doing anything, and this one, like 0 1, we are going to add some angle. Okay, and this you need to understand, little bit misleading, but it's very simple thing. So when this we says 0 1, what is this? This will be 1 0, because we are having two X gates, and the 1 1 will be achieved in this place. So this is important. Okay, all right. So when you execute in a simulator, I just try to run this circuit in simulator and plotted the results as you have seen earlier in the slide. This is 0 0 0 pixel, and this is 1 1 pixel, which is white, and this is fully black, and the other two pixels, one has got equal black and white, the other one is having dominant black and less white. Okay, and NEQR encoding slightly different, as we know that we have two registers, one for indexing and another one for intensity. So again, as we have seen it in the slide, we will be having 8 qubits. Okay, so we have created the number of qubits, and here we are just showing identity gate for the intensity one, and for indexing we have to have Hadamard gate to generate 0 0 0 1 1 0 1 1, right? The superposition states for these two qubits, and this you don't have to do, but just for looking back, look, we have added I gate, or identity matrix. And for 0 0, we have seen earlier, we don't have to do anything, but again for better look, we have put I. And for the other two states, 1 0 and 0 1, we need to add intensity like this. For example, this is 0 0 1 1 0 0 1 0 0, like that. And for the next one, it is what 1 1 0 0 1 0 0, like that. And the last one is all ones, correct? That is what is being done here. Okay, so now if we make a measurement, you will be able to see the pixel number representation. 00 is the first pixel, 01 is second, 10 is third, and 11 is fourth, and the corresponding grayscale intensity. So you can see it's a very perfect one. There is nothing can go wrong, unlike the previous one where we have angles. So this is also being widely used. Okay, so now we'll go back. So to summarize, we were able to encode the given image in three different formats, and we were able to get the edge detected image with one approach. Like that, you can come out with different approaches. And these are all the references, as I told you, QISKIT. I mean, the entire code I have taken from QISKIT. Okay. Except that maybe I removed some text in between. Otherwise, there are two pages, one which gives the representation, the other one gives the edge QPIE and the edge detection algorithms. Okay. All right. And these two papers are really good. I think they are the authors of the different methods, what we studied just now. And this one is good for the edge detection. Okay, so if you still think that something I missed out, you can see these references. All right, so what's next? Yeah, well, you continue to work on quantum computing, come out with some fantastic algorithms. Also, I request you to suggest some similar topics that will be useful to you. And I'll come back with some more videos. Actually, I'm really interested in quantum image processing. So I'll learn more about image recognition, filtering, and image compression and things like that. So hopefully I'll be able to come with my videos soon. So till then, bye bye. Thank you for watching this video.